Here's a video discussing chapter 11 from the textbook. This one's on sampling distributions, which we covered on Wednesday, November 10th. And sampling distributions kind of goes back to normal distributions, which we've discussed before. So we have discussed the difference between parameters and statistics. A parameter is a number that deals with the population. A statistic deals with a sample. So a parameter would be what percentage of people voted for Joe Biden in the 2020 election of the actual election. We actually have those results. But a statistic would be if you had a sample, like so prior to the election, if we took a sample of like say 1,000 Americans and randomized it, hopefully, and said, how are you going to vote? And then we look at the percentage of people, that would be a statistic that would vote for Biden if it's from a sample, but parameters from the whole population. So we look at this here, this example, the mean income of this many households contacted by the current population survey was this. The number is a statistic because it's from a sample, right? The population poll wants to draw from is includes about all 170 million U.S. households. The primary interest is the actual mean income, and we don't know this because we haven't investigated, but I'm sure maybe there's some database where we could probably figure that out. And we use different symbols. If you use population mean, it's mu. Population standard deviation is sigma. But sample mean would be X bar, and sample standard deviation would be just the letter S. And you have like a problem we'll work out here. Like here, here's an idea for treating advanced melanoma, the most serious kind of skin cancer, genetically engineer white blood cells that better recognize and destroy cancer cells. Then infuse these cells into patients. Subsequent small study of this approach were 11 patients whose melanoma had not responded to existing treatments. One outcome of this experiment was measured by a test of the presence of cells that trigger an immune response in the body and so may help fight cancer. The mean counts of active cells per 100,000 cells for the lowest subject were 3.8 before infusion, 162.2 after infusion. So this is, again, from a sample. So if each of the bold-faced numbers, that's going to be a statistic, right? And again, 11.1, the answer key is at the end, just like chapter 9.1. And you can see they are statistics because they relate to a sample, right? So that's 11.1. Again, you're only doing odds. Then we talk about the law of large numbers, that if you have a large enough sample, that ultimately it should model the population, right? So that's what that's saying there. There's an example you could read through. So again, you draw observations at random from any population with a finite mean. As the number of observations drawn increases, the mean X bar of the observed values gets closer and closer to mean mu of the population. One good example could be what if we know, for example, the mean age of all students at Sacred Heart Prep, right? We could, I could easily go into our database, 600 plus students at Sacred Heart Prep, and I could just find the average. Now, what if I decide to pick, make a random sample from the school population and try to find the average age? If I only do like 5 students, it might be pretty far off, right? Because maybe what if I pick 5 seniors, right, by chance? But as I increase the sample size, like say now I go from like 5 students to like 10 or 20 or 40 or 50, or even 100 students, most likely it's going to get pretty close to the true mean. Or in gambling, sometimes you can see they talk about gambling off to the left. That's always a fun topic. The game of roulette, like for example, if you played roulette 1,000 times, odds are you would probably hit black almost 50% of the time and red almost 50% of the time. If you play 10 times, maybe hit black all 10 times, right? So once you do something enough number of times, ultimately the sample will start looking more like the population. And here's an example that talks about that stuff. And then a problem to work out that you'll do here. Sampling distributions. Usually we try to take a large number of sample sizes of 10. 10 is usually considered a pretty good number to go. I'd like to say 30 is probably a little better. Calculate sample mean, try to make a histogram, explain the shape of the histogram. We've done that in the past. And as you take more and more samples of size 10, you'll start noticing that ultimately the distribution is going to start looking more normal. We talked about this. So the population distribution is obviously what we expect for all individuals. So say, for example, I made a histogram of all the people's ages at Sig Prep. I mean, we figure some people might be 14, some people might be 18. So if I did a sample of, say, 10 students or say 20 students, but did over and over and over again, ultimately the distribution will start looking more normal. The sample distribution is, again, just you take all possible samples of the same size and the same population. So you just do it over and over again. Shape, obviously we're looking for normal, like a bell-shaped curve. Center, you want the mean to be right in the middle. And the spread, you want to make sure that 68% of your data is within 1 standard deviation of the mean. That would mean that you have a normal distribution. And then we have some more problems to work out. And sorry for the slight interruption. My son was chasing my daughter around with a toy alligator. So anyway, that's the joys of parenthood. So okay, so sorry again for that disruption. So yeah, so when you're dealing with standard deviation of a sample, you want to do sigma divided by root n, where sigma is the population standard deviation. Because if you have a sample of just 1, the standard deviation, well, the bottom line is that if you have when you're doing a sample, when you have a larger n value, that actually will reduce the standard deviation, and actually will start, you know, making the distribution seem a little tighter. That's kind of what's happening. So the averages become less variable than individual observations. The results of large samples are less variable. The result of small samples. So that's why we do that for our sample standard deviation. We do sigma over root n. And that's what you actually would feed into the calculator if you wind up doing second vars, option 2. You start looking to lower and upper. And then we do the mean. We write that more nicely, the mean and sigma. You actually will take your sigma and divide by root n being the numbers of the number or your sample size, how many individuals you have in your sample. And you can see that when n gets larger, we tend to see a little less variation and a tighter distribution. So we have some problems that you'll work out here. Let me actually work out 11.9 really quickly. So you see the means 186, and we're looking at a blood cholesterol level for all men from ages 20 to 34, and you look at standard deviation of 41. So you have a simple random sample of 100 men. What is the sampling distribution of X bar? X bar is a sample mean. What is the probability that X takes between 183 and 189? There's a probability that X bar estimates plus or minus 3 of the mean, right? Because the mean is 186. So what you'll do, your sampling distribution will be X bar, which is 186, plus or minus root 41. Sorry, oops, I meant to say 41. Plus or minus 41 over root 100. Root 100 is 10, so it's 186 plus or minus 41 over 10, or 186 plus or minus 4.1. So that's going to be our distribution. So you want to know what's the probability that you'll find someone between 183 and 189. Maybe that's considered a healthy range, perhaps. So what you're going to do is we're going to go to our calculator, our trusted calculator here. Just give us some time to warm up here. So again, second vars, option 2. I'm going to do 183 and 189. And the average number is 186. And I'm going to do 41 over root 100. So my distribution ranges from 186, from 190.1 to 181.9. I want to know what percentage would be between 183 and 189. So if I do this really quickly, So it's about 53.6%. That's what I'd expect. And if I go to the solution key just to check to make sure I did this correctly, hold on a sec. Got to pull the right stuff up here. Yep, 53.46. That's part A. And then part B, they change it to 1,000. So if I go back and change that to 1,000, and don't mind if my kids start yelling again, because I think that's going to happen any minute now. If I do this again, so I get 97.9%. And if I go to the solution key, you see I get 97.9%. So there we go. That's actually very accurate. So yep, that's how that works out. Yeah, the central limit theorem kind of just tells us that if you draw some random sample size, n from a population mean mu, and find a standard deviation, the central limit theorem states that when n is large, the sample distribution will follow a normal behavior or a bell-shaped curve when you start taking large samples. So there's just some questions on that, some problems you do there. Then you have the summary and what all these terms mean and represent. Again, you're only doing the odds. And you can do multiple choice questions. And also, we have you do some of the free response up to 11.27. So go up to 11.27, but only odds. And you have the answers on the following page. And that ends the video.